Today we're going to look at chapter 4.8, acid-base reactions. I have some notes to go over and then I have some example problems to do. You should take notes and then you'll have a worksheet to complete with problems. So acid-base reactions are also called neutralization reactions. And so we will cover acid bases in more detail in chapters 14 and 15 next semester. But we're looking at reactions that form water. They don't form a precipitant like we talked about in 4.7, but they do form water, which water is composed of hydrogen ions and hydroxide ions in solution. We want to go over a definition of an acid base, and we want to go over the Bronsted-Lowry definition. So according to the Bronsted-Lowry definition, an acid is a proton donor. A base is a proton acceptor. I'm trying to get some space in my paper here. So let's look at a strong acid and strong base neutralization reaction. So I'm going to write the formula equation first. So in this example, I have hydrochloric acid, strong acid, reacting with sodium hydroxide. And that's going to form, so the acid is the proton donor, so a proton is a hydrogen ion. And so if I go back up here, hydrogen ion is a proton because it's just made up of a proton. So hydrochloric acid is the acid because it's going to donate a proton over here. You're going to get water, and I'm going to write it as HOH plus sodium chloride. And so for the complete ionic equation, you would have hydrogen ions plus chloride ions plus sodium cations plus hydroxide anions forming water plus sodium cations plus chloride anions. And so you take out your spectators, which are the sodium ions and chloride ions, and you're left with your net ionic equation. Which is hydrogen ions reacting with hydroxide anions to form water. And you can write it as H2O. You don't have to write it as HOH. So then let's look at a weak acid and strong base reaction. So for this equation, for our formula equation, we're going to have acetic acid, which is in vinegar. It's a weak acid. It does not completely dissociate. Plus sodium hydroxide, a strong base. And that forms water and sodium acetate. So I'm just going to write the net ionic equation. This hydroxide ion is this sodium hydroxide is a strong base, so it completely dissociates, forming hydroxide ions and sodium cations, but this does not. This is a weak acid. It only partially dissociates. So your net ionic equation you would still have some acetic acid molecules plus hydroxide ions, and that would form water, plus there would be some acetate ions. This is a weak acid. It does not completely dissociate. Into hydrogen ions and acetate ions. Sodium hydroxide is a strong base, so it does completely dissociate. So when you have acid-base reactions, you will do acid-base titrations. And we will do a titration in the second part of Chapter 4 with sections 4.9 through 4.11. And so titration, you're doing a volumetric analysis. And so this is a technique for determining the amount of a certain substance by doing a titration. And so a titration is delivery from a burette of a measured volume So measured volume with a node concentration. This is called a titrant. Into a solution containing the substance being analyzed. And that's called the analyte. And so if I draw a little picture, and I'm not great at drawing pictures, but you would have your flask. And this is the analyte. Plus it would have an indicator. And then you would have your burette. And this would have the titrant in it. The burette has, the titrant has the known molarity, and you measure the volume. For the analyte, you start with a specific, you start with a volume. So you know or you measure the volume and you calculate the molarity. So when you're doing these titrations, you would have the equivalence point. It's also referred to as the stoichiometric point. And this is the point where enough titrant has been added to react completely with the analyte. At the equivalence point, your moles of acid equal your moles of base. Now, the only way to see the equivalence point is to look for the endpoint. And so this is the point where the indicator changes color. So when I drew my little picture here, I showed you the analyte has an indicator. The indicator needs to be picked carefully. You need to choose an indicator that changes color exactly at the equivalence point. And so when you look at indicators, they have a pH range where they change color, and so you can determine what pH range or equivalence point is going to happen at, and then pick the appropriate indicator to use for that color change. The endpoint, you don't want to add too much of your titrant where the color change is so dark, because then you've overshot your endpoint, you want to make sure it's a light. For example, when you use phenolphthalein, it turns pink. It wants to be a light pink persistent color. So what we're going to do now is a few calculations since we've gone through some of the notes. And so the first example problem, what volume of 0.100 molar hydrochloric acid will react, I should say will, react completely with 50.00 milliliters of a 0.200 molar sodium hydroxide solution. So first I need to write my balanced chemical equation. I have hydrochloric acid, strong acid, reacting with a strong base. It'll form water and sodium chloride solution. Now, if you look at this equation, it's 1 mole of acid reacts with 1 mole of base. It's a 1-to-1 mole ratio. So for that reason, we can use the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And so we had from our notes, we wanted to find the volume of the acid. It's 0.100 molar. And we know the sodium hydroxide, we had 50 milliliters of a 0.200 molar solution. So we have 0.100 molar hydrochloric acid, some volume of that equals the molarity of the base times 50 milliliters of sodium hydroxide. So when I do that calculation, my volume of my hydrochloric acid equals 100. I need 3 decimal points, so I need 3 sig figs, so put a decimal point there for 3 sig figs milliliters of HCl when you solve for the volume of the HCl. So for our next problem, a student titrates an unknown amount of potassium hydrogen folate, abbreviated KHP, with 20.46 milliliters of 0.1000 molar sodium hydroxide solution. What mass of KHP was titrated by the sodium hydroxide solution? And I gave you the molar mass. So first we're going to write the balanced chemical equation for this reaction. And so this is the acidic hydrogen that is donated to the sodium hydroxide. So I'll have water and so we don't know what the mass of this is, but we know that we have 20.46 milliliters of the base and it's 0.100 molar solution. So what we're going to do is, I'm going to kind of show you a little flow chart. We're going to convert this to moles of sodium hydroxide. And then we'll use the mole ratio to convert to moles of KHP. And then we can use the molar mass to convert to grams of KHP. So I'm going to start with my 20.46 milliliters of sodium hydroxide. So that I can work with my molarity, I'm going to convert from milliliters of sodium hydroxide to liters of sodium hydroxide. And then convert from liters of sodium hydroxide to moles of sodium hydroxide. That's my molarity, that if I have, for this solution, I have 0.1000 moles of sodium hydroxide for every 1 liter. Then I can convert from moles of sodium hydroxide to moles of KHP. This is a 1-to-1 mole ratio. And then I can use the convert from moles of KHP to grams of KHP. And this is the molar mass that was given to us in the problem right here. So you didn't have to calculate it for this one. If it wasn't given to you, you would have just calculated the molar mass. And it's 204.22 grams. So you're going to multiply the top, multiply the bottom. You can put a 1 here as a placeholder if you want. Multiply the top, multiply the bottom, divide. I would pause your video and try this out. 4 sig figs, 4 sig figs, 5 sig figs. So I need 4 sig figs in my answer. These units cancel. So that I'm left with grams of KHP. And I need 4 sig figs at 0.4178 grams. The last example I'm going to do, what volume of 0.0200 molar calcium hydroxide solution is required to neutralize 35 milliliters of a 0.0500 molar nitric acid solution? And so I'm going to write my balanced chemical equation first. I have calcium hydroxide. It's a group 2 metal hydroxide, so it's a strong base. Nitric acid is a strong acid, excuse me. It will form, because the nitric acid is a proton donor, it'll donate a hydrogen over here. It'll form water and calcium nitrate. So I do need to balance this. I have 2 nitrates on the product side. I have 1 on the reactant side, so I put a 2 here. Now I have 2 hydrogens and 2 hydroxides. So I have 2 hydrogens plus 2, that's 4 hydrogens. So if I put a 2 here, that gives me 4 hydrogens, and it balances my oxygens at 2. So if you notice, this is not a 1-to-1 mole ratio. So we can't use that moles of acid times the volume, molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. We're going to have to use some stoichiometry. So I'm trying to find the volume of calcium hydroxide. I know it has this molarity. I know that I have 35 milliliters of nitric acid, and I know it's this concentration. So what I'm going to do, kind of make a little plan, I'm going to convert this to moles of nitric acid. I'm going to convert from moles of nitric acid to moles of calcium hydroxide. And then from moles of calcium hydroxide, I can convert to the volume of calcium hydroxide using the molarity. So I'm going to start with my volume of nitric acid, my 35 milliliters of nitric acid. I'm just going to put a placeholder here. I'm going to convert from milliliters of nitric acid to liters of nitric acid so I can work with the molarity. 1 liter is 1,000 milliliters. Then I'm going to use the molarity that was given, convert from liters of nitric acid to moles of nitric acid. 1 liter, 0.0500 moles. So I'm here, moles of nitric acid, so I can convert from moles of nitric acid to moles of calcium hydroxide. And that is 1 mole of calcium hydroxide reacts with 2 moles of nitric acid. Then I can convert from moles of calcium hydroxide to liters of calcium hydroxide, which is the molarity. 1 liter is 0.0200 moles. And then finally, I'm going to convert back to milliliters. And so we have done everything. We've converted from milliliters from the volume and concentration of nitric acid to moles of nitric acid here. And then we convert it from moles of nitric acid to moles of calcium hydroxide here using the mole ratio. And then we convert it to the volume of calcium hydroxide by using the molarity. And so you want to try this on your own paper. You're going to multiply the top. I would do that in parentheses. Multiply the bottom. Divide. Units cancel. So I'm left with the units I want, which are milliliters of calcium hydroxide. Looking at sig figs, I have 4. I have 3. I have 3, so I'm going to need 3 sig figs. You get 43.8 milliliters of calcium hydroxide. You have some practice problems to complete for this section. We will go over this in our full Zoom meeting at the end of the week. Message me with any questions or concerns.